Hey guys, welcome back to Matrix Algebra. I wanted to make a quick follow-up video to last night's pitiful video, if I do say so myself. I am embarrassed about how sleep deprived I was and how my performance was not really that good. So I slept for 14 hours last night, so if this video isn't up to standard, then I think I deserve to be flogged in the public square in front of everyone. So hopefully this will be up to standard, up to quality. So we talked a bit about matrices in the last video. We talked about what they are, what they look like. We talked about different operations on matrices. We learned how to do matrix multiplication, matrix addition, and then we learned about how to multiply a scalar multiple by an entire matrix. And that's something else we talked a bit about. We talked about the distinction between a scalar and a vector. So remember that a scalar is a quantity that's only a magnitude. Remember that a vector is a magnitude and a direction. And I understand that some pre-calc classes don't really go in depth about vectors, but I feel like in this particular video, I wanted to give some information on that topic. I wanted to shed a little bit of light on vectors because vectors are going to help us understand matrices a lot better. The two concepts really go hand in hand. So let's talk about vectors for a bit. And I feel like the best way I can possibly explain a vector is with a visual aid. And you probably know by now that no matter how much sleep I get, this drawing is going to be horrible. So don't expect anything else from me. So I have my 3D coordinate system. Typically, we're used to seeing things like this. We have an x-axis, we have a y-axis. But for purposes of this demonstration, I'm going to add a third axis. This is going to be our z-axis. And sometimes they do things a little bit differently. Sometimes certain math teachers will have this be x, and then this will be y, and then this will be z. But I'm just used to having it the other way around. So I'm going to have x be the place it normally is. Same goes for our y-axis. And then this right here is our z-axis. So let's talk about how to draw things in 3D space. So we're really good at drawing things without this third dimension being here. Like, for example, we're good at drawing points on the plane, on the two-dimensional plane. We're really good at drawing lines. We're really good at drawing graphs of other distinct functions. But what the heck are we supposed to do when we have this third dimension? So things work a little bit differently in 3 dimensions. So I want to show you guys the intuition for drawing a vector in 2 dimensions first. So I guess I kind of jumped the gun on that one. I should have introduced z so early. But I want to show you guys how to draw a vector in 2 dimensions first. So what is a vector anyway? So we know that a vector is a magnitude that includes a magnitude and a direction, a quantity that includes magnitude and direction. And let me just write some of this stuff down in case you're not too sure about some of these vocabulary words. I want to make sure I have these written down so that we have a clear understanding of how to spell everything and we have a good picture of what each of these things really means. Because linear algebra is really, really abstract. It introduces a ton of new vocab. I remember taking Math 330 a couple years ago. Geez, I'm old. It's just starting to hit me just how old I am. Ouch. So took linear algebra a few years ago, and I just remember being totally overwhelmed with this new vocabulary being thrown at us. I had to have like my own linear algebra dictionary I pulled up on my iPad, and I had to look up words every few minutes when I was studying for a test or learning new material. So it is very, very vocab intense. So I want to make sure that I write down all of these words and maybe give a brief definition. Nothing too fancy, but something that will help us understand the basics of what I'm talking about. So a vector is a magnitude that includes, I keep saying the wrong thing, a quantity that includes a magnitude and a direction. And I just moved into a new apartment and the Wi-Fi here is horrible. So if we have a less than average video quality, that would be why. I refuse to accept the blame for that one. It's just my new apartment and the Wi-Fi is horrible. I'm actually considering moving to a new place just for the Wi-Fi because this is such an important part of my job. I have to have Wi-Fi in order to do my work, so I don't have very many options. So we have a vector. It's a magnitude that includes a quantity that includes a magnitude and a direction. So it's really hard to understand what this really is without an example. So an example would be, well, there are a few different ways we can express a vector. So let's say we have the matrix form of a vector, 1, 1. So whenever we have this in 2 dimensions, this would be the first dimension on top, this would be our x. This would be the second dimension on the bottom. This would be our y. So this notation for vectors is telling us that our x component, that's what we call this top number in the matrix notation for a vector. We call this our first component. Vectors have components. And components to vectors are like elements to an array. I guess maybe make it a little less general, matrices. They're like elements in a matrices. So a matrix has elements in the same way that a vector has components. So instead of these two ones being called components, or instead of them being called elements, in vector notation, we call these components instead of elements. So x and y are both components. So another way we can express the same exact information would be using another vector notation. We could call this I with the little hat on it. We call this I hat plus j hat. And then the other one that's used quite a bit would be this right here. We have angle brackets like this, and then we have both components separated by commas. So these are the three main notation conventions for expressing vectors. So now let's talk about what a vector looks like on the plane. So we can tell that we have two components in our vector. The x component always appears first. The y component always appears second. So x is 1 and y is 1. So I'm going to draw this vector on the 2D plane. So x is 1, y is also 1. So I'm going to make a dot right there. And then a vector looks like this in the coordinate plane. It's always going to be an arrow pointing at a particular location. And it's interesting to note that without the arrow, it's not a vector. So if we have this is not a vector. It's just a line segment. It has to have the arrow for it to be considered a vector. So let's try something else. Let's try drawing another two-dimensional vector, if I can do this without screwing up too badly. I almost feel like being one of those clickbait YouTubers that say, slap like now to give me the power to draw this properly. No pressure. So I think what I want to do next is I want us to practice drawing this vector right here, -1, 2. But before we draw this one, I want to show you guys how to do the other naming conventions for this vector. So I want to write this in the same 3 ways we wrote the other one. So we have our first one completed. We have our matrix notation for our first vector written nicely. So now I want to do the same thing for the other two conventions. So we have, this is going to be -1 times I hat. And then this is going to be +2 times j hat. So let's talk about what these I hats and j hat things are really quick. So we call these unit vectors. So I think it's worth our while to talk about this a little bit. It's going to come up quite a bit later on. That is pitiful. I hat and j hat. I think I'm going to type some of this. My OCD is going to be off the charts because I have some stuff typed and some stuff written, but my handwriting is so deplorable, I think it's just better to do it this way. So I and j hat are unit vectors. Can't spell today, or on any day, I guess. So we pronounce these I hat and j hat. They're unit vectors. So we have a decent understanding of what vectors are by this point. We've covered a little bit, but what does the word unit mean? So the thing about math in a lot of different areas of the world is it is heavily influenced by language, and in Latin Latin. Really, I can't talk again. Tongue-tied. It's influenced by a lot of Latin. You see a lot of mathematical vocabulary peppered with quite a bit of Latin. And You might notice in other industries as well. I think chemistry and physics, and especially political science and the law, you have things like habeas corpus, e pluribus unum. Latin makes an appearance in a wide variety of academic disciplines, and math is no exception. There is a ton of Latin all throughout math. So the word uno, I'm going to go off on one of my famous tangents. So the word uno, we know is Spanish for one. We know that a unicycle. So let's see if I can draw something that even closely resembles what I think a unicycle looks like. No promises that this is going to turn out well. I guess that's it. That's not too bad. I guess you might need another pedal, but that's my budget unicycle right there. That's the store brand unicycle. So a unicycle has one wheel. So they both have un. Uno means one. It's Spanish for one. And in fact, un on its own is French for one as well. So uno and un both mean one. The un prefix in a unicycle tells us how many wheels the unicycle has. It has one wheel. So what do you think the word unit means in that case? It has that same un prefix. So un, we can tell pretty clearly it means one. It's the Latin root word that means one. Another one of those would be mono. Like a monomial, for example, is a polynomial with just one term. But un is definitely more common of the two naming conventions. So a unit vector is a vector that has a length of one. So I want to just define that real quick. So a unit vector has a length of one. So I want to ask you guys, what do you guys think about this vector that I drew? Do you think this is a unit vector or is this not a unit vector? So you might be thinking, hey, Justin, there's a one right here. The x has a length of one, and then there's a one right here as well. So yes, this is a unit vector. You're on the right track, but not quite. This one is not a unit vector, and I'll show you how I know that. So we're going to use something called the Pythagorean theorem, something we're all pretty familiar with by this point, to see what the length of this vector is. So it's important to note that the height is not part of the vector. And if we draw a line here, this x part of this is not part of the vector either. The vector is only the diagonal part. So I'm going to use a triangle to help us find the length of the vector. So we have a base of our triangle as 1, height of the triangle is 1. So then if we do the Pythagorean theorem, we can tell that we have to have a hypotenuse of the right triangle that's square root of 2. So yay, we've successfully found the length of our vector. So the length of this vector is square root of 2. So this is not a unit vector. A unit vector has a length of 1. This has a length of square root of 2, so it is definitely not a unit vector. So now that we have this, let's go ahead and write this vector into other naming conventions. So we have I hat and j hat are unit vectors. So it looks like our I component in this one is going to have to be -1. So x always appears on top. X corresponds with I hat. Y always appears on the bottom of a two-dimensional vector. And then the y corresponds with j hat. So what we really have here is we have -1 I hat plus 2 times j hat. J hat is the unit vector in the y direction. And then we just have one more. First component in this naming convention would be -1, and then the second component is 2. All right, so we've written 2 different vectors, 3 different ways. Now let's go ahead and draw the second one on the plane. So I invite you to pause the video, bust out a sheet of paper and a pencil, and then see if you can draw the second vector, and then come back to see if you did it properly. It's one of those things where you have to kind of just learn by doing. I learned this personally when I took linear algebra. My teacher was super intelligent, really, really smart guy, really humble, really down to earth, one of the smartest people I've ever known. I loved listening to him teach linear, but just sitting and listening to him teach for an hour wasn't enough for me. I had to kind of learn by doing. I had to do example after example, reviewing vocabulary after vocabulary word until I felt like I had a sufficient understanding of the material. And sometimes even seeing one definition wasn't good enough, especially when I got into a topic called eigenvalues and eigenvectors. I had to read maybe 3, 4, 5, 6 different definitions of the same word before I had that aha moment, that light bulb moment, and I finally knew what the heck the teacher was talking about. So if you don't understand this stuff right away, you are far from alone. I'm in the same boat. So don't give up, keep going, keep trying, and you'll get the hang of this before you know it. So like I said, pause the video right now. I highly invite you to draw this vector on the plane and then come back to see if you did it properly. All right, let's take a look. So I want to start by identifying the x component of the unit vector. So we have I hats, our unit vector. We have that unit vector times -1. So the x component is -1. And then we can tell the y component, which is the coefficient of our j hat unit vector, would be 2. So this would be the y part of the vector. We're going to go up 1, we're going to go up 2. So then now that we have the x and the y mapped out, we want to draw the place where we think the vector would go. So we want to put a dot on the place where the x and the y meet. And then we're going to draw a vector straight from the origin to this point. So that's how we drew it. That's how we draw a vector. So we had something like this for the first vector, and then we have this for our new vector. So that's how we draw vectors. Let's talk about how we add vectors. So vector addition is actually pretty similar to matrix addition. There are a lot of commonalities, a lot of similarities between vectors and matrices, aside from just the notation. You can add them in similar ways, and you can multiply them in similar ways too, only if you have the right circumstances. I'll get a little bit more in depth about what that all means, either in this video or maybe a few videos down the road, but we will get there eventually. Let's talk about how to add vectors together. So let's talk about what we call vectors real quick. So we have all these really cool naming conventions. Let's talk about what they look like in equation form. So in algebra, we're used to variables, we're used to constants, we're used to polynomials that feature constants and variables in similar terms. So vectors typically have this kind of a convention. V and U, for some reason, are really common in vector notation. So this is how we name a vector. We have a variable, and then we have this little arrow pointing to the right. And we say this vector is equal to something with x and y both being 1. And then because we already used v for our first vector, I'm going to use u for the second. Some people will use u first and then v. For some reason, I'm used to doing it this way. Not sure why, but it doesn't make that much of a difference. So now that we have our two vectors defined, let's see if we can do some vector addition real quick. We're going to add vector u and vector v together to get a sum. So we're going to add everything component by component. We have 1 plus -1 for our first component, and then we have 1 plus 2 for our second component. First component on top, second component on bottom. So when we add these together, we get 0 for the top, and then 3 on the bottom. So if we add these together, we get this vector right here. We get 0i hat plus 3j hat. So that's not the only way we can add vectors. We can also add vectors graphically. We did it algebraically. Now let's learn about how to add vectors graphically. So I think I want to have a bit more room on the coordinate plane. I'm going to maybe draw a new one real quick. Make sure we have enough room for this. So we found the sum of these two vectors algebraically. Now let's find them graphically. So the way we add vectors graphically in the Cartesian plane like this is we draw the first vector. So our first vector is 1, 1. I'm going to go ahead and draw that vector for us right now. Perfect. And then after that, we want to draw vector u. But the thing is, we can only add vectors head to tail. So this would be the tail of our first vector. This right here would be the head. This is the arrowhead, so we consider this to be the head of the first vector. We can only add vectors head to tail. So that means when we draw the second vector, we have to start where the first one left off. So we're going to start right here when we draw our second vector. So it looks like our second vector has an x component of -1 and a y component of 2. That means we're going to go 1 to the left, and then we're going to go 2 up. So we're going to go 1 to the left, and then we're going to go 1 up, and then we're going to go 2 up. So we're going to start where we left off for the first vector, and then we're going to draw a line. We're going to draw a vector that starts right here and then ends all the way right there. So we have this. And let's see what the coordinates of this point are going to be. So we can tell that x is 0. We can tell that y is 3. Hey, that seems kind of familiar. Mind blown. So we got the same answer graphically as we got algebraically. So when you take linear, or even if you take algebra 2 or pre-calc and you learn vectors in those classes, teachers usually have their own preferred way of adding vectors. Like, for example, if you're doing a test, they will tend to be very, very clear about if they want you to add them graphically or if they want you to add them algebraically. So it's a really, really good idea to know how to do both of those things effectively. So let's get back into multiplication. So remember with matrix multiplication, we have certain conditions that allow us to multiply vectors together. So this vector, how do I keep saying vector when I mean matrix? That allow us to multiply matrices together. So this matrix has 2 rows and it has 3 columns. So is it possible to multiply this vector by this other vector, tu, v, w? Is it possible to multiply, did I really say vector again when I mean matrix? I'm losing it, guys. So this is our first matrix, it's 2 by 3, and then our second matrix is 2 by 2. So is it possible to multiply these two together? And remember, for us to be able to do matrix multiplication, the inner dimensions must match. They don't match, so we're not able to multiply these matrices together. We are not able to do the matrix multiplication. But is it possible to multiply a matrix by a vector? Under certain circumstances, yeah. So let's walk through an example. Let's say we have this matrix. Let's call this matrix A. And let's say we have vector, I'm going to call it vector x. And remember, the vector has to have that little arrow on top. This is a vector. We call this a column vector because it's just a skinny matrix with 3 elements corresponding to components in the vector. So x hat is a vector, but plain old x without the, or I meant to say x with the arrow on it is a vector. This plain old x without the arrow is just a variable. So we're going to treat this x the way we normally do. We're going to treat this x on the outside as a vector. And then we're interested in solving this equation. But before we even write the equation, I want to define vector b, vector lowercase b. If this stuff doesn't make sense right now, it will in a few minutes. Don't you worry. So this is more of a linear algebra topic, but I really, really want to show you guys how this process works to help you understand why vectors and why matrices are such a really useful tool to use and to have in your disposal. So we're really, really interested in solving equations like this. So one of our main goals in a typical linear algebra class is to solve for this vector x. So A is a matrix, x is a vector, b is a vector. So a matrix times a vector gets us another vector. So how the heck do we solve for a vector? Well, if it were something easy like this, so if A were just a number, and we have x and then b is just another number, we're really, really good at this. but things get a lot more complicated when we don't have just variables and we don't have just constants. We have a matrix times a vector gets us another vector. So let's write this in matrix vector form to understand what's really going on in this equation. So we have our vector times x. X is our first column vector. Equals our other column vector, b. So if you watched the matrix video I posted last night, you might have a decent idea on how to solve this. So I invite you to pause the video, definitely give it a try, see if you can find x, y, and z for us. If not, just wait for the explanation. We'll do it together. All right, so let's go ahead and see if we can actually multiply these things together. So we can multiply a matrix and a vector in the same way we multiply a matrix and another matrix. We have to see if the dimensions on the inside match. So this first matrix, this only matrix, I should say, is 3 by 3. And then our vector, our column vector directly to the right of it, has 3 rows and 1 column. So this is a 3 by 1. So we meet the first criteria needed for multiplication. The inner components, the inner dimensions match. So that part's good. We're clear to do the multiplication. And then let's just confirm that we have the right dimensions in the product. So we have on the outside, we have a 3, we have a 1. In our result, we have 3 rows and 1 column. So perfect. Everything works out exactly the way we want it. Perfect. So let's remember how matrix multiplication works. So it's not like normal multiplication. Things work a bit differently. So we want to highlight the first row of our matrix and then our column vector. And this time we have a result. So we're used to doing things. Hang on a second. Let me go off on a quick tangent, one of my famous tangents. So by this point, we saw something like this in the last video. In the last video, we multiplied this row by this column, and then this row by the same column, and then this third row by the exact same column, and we got a vector as a result. We're doing things a little bit differently this time. We're going backwards. We are reverse engineering a solution, so we can find the vector when we multiply this. When we multiply by our matrix, we get this as our result. So we're going to multiply our first row by this column vector. So we have 1x plus 1y plus 1z equals 6. All right, now we're going to move on to the next row. We have 0x plus 2y. You know what? I think I'm going to use different variables. I'm going to use a, b, and c. I apologize about kind of being all over the place, but then again, it's probably what you're used to by now. So we have a plus b plus c equals 6. Oh, and then I forgot to change this. And then we have 0a plus 2b plus 5c equals -4. Then we have 2a plus 5. Whoa, what was that? It's not 5. Plus 5b minus c equals 27. So then what the heck are we supposed to do here? Things are kind of complicated, a little bit confusing. So what we want to do now is maybe put this matrix in a reduced form. We want to get this to the identity matrix if possible. So let's go ahead and see if we can reduce this into our lowest possible echelon form. So this is kind of a continuation of what we did yesterday. I showed you guys how to do row operations on a matrix to make it simpler. So I want to leave the first row alone. I'm going to swap row 2 and row 3. So row 1 gets left alone. I'm going to swap these two rows. So I'm going to have 2, 5, -1. And then I'm going to have 0, 2, 5. And then from there, I'm really interested in making this 2 into a 0. So what I'm going to do is I'm going to multiply the first row by 2, or I'm going to multiply the first row by -2, and then add that result to row 2. So -2 times row 1 plus row 2. That would get us our result, and then the result replaces row 2. So we have 1, and then 1, and then 1. And then I'm going to multiply this by -2. We get -2, and then I'm going to add 2 plus -2, which is 0, and I'm going to replace this 2 right here with the result. I'm going to replace it with 0. So then we have 5 plus -2, we get 3. Then we have -1 minus 2, we get -3. All right, next thing I want to do is I'm really interested in making this right here. Remember from our last video that we call this one right here, we call that a pivot. So whenever we have one single column with a 1 and then only zeros, we have 1, 1, and then a bunch of zeros and nothing else, we call that a pivot column. A pivot column only contains a 1 and a bunch of zeros. So we have our first pivot. So we're interested in turning this 3 into another pivot if possible. So how do we do that? We're interested in making this into a 1 first of all. So a quick way to do that would be to take the entire row 2 and just divide it all by 3. So we're going to do row 2 divided by 3 gets written to row 2. So 0 divided by 3 is going to be unchanged. And then we're going to have 3 divided by 3 is 1. -3 divided by 3 is -1. So we're going to have 0, 1, -1. And each of these can actually be thought of as a vector. So this is a column vector. This is a column vector. This is also what we call a column vector. So a column vector is just a vector that forms a matrix. So we have 3 column vectors that make up this matrix. This matrix A is made up of 3 column vectors. And I'm going to be making linear algebra videos a little bit in the future. This is a pre-calc video, so I don't want to get too hardcore with the terminology. But in the linear algebra video, we're going to be talking about things like basis and span. We're going to be talking about how to create a basis set of vectors that span a certain space. That could be R3, could be R4, could be R5. We're going to be solving something in terms of eigenvectors. We're going to be doing something kind of like this. So this isn't going to be part of the pre-calc series. This is going to be part of a new series I'm going to be doing a little bit later called the linear algebra series. We're going to be dealing with what I consider to be the really hardcore topics of matrix algebra, the things that are really super abstract and hard to understand. But for purposes of this video, we won't be getting into any of that. So back to this matrix that we're simplifying. So we have a 0, 1, -1. So what I want to do next is I want to take this first row. I'm interested in making this into a 0. So let's think about a way we could do that. Before we do that, I'm going to move things over quite a bit. Give us some extra room. So how do we turn the second element in the first row into a 0? So I think the best way to do that would be to take the entire second row and then subtract it from the first row. Or we can also think of it as doing -1 times the second row plus the first row gets added to the first row. So this 1 is going to be unchanged. We're going to have 1 plus -1, we get 0. Then we're going to have 1 minus negative 1. That's going to get us 1 plus 1. We're going to get 2. And then second row is unchanged. Third row is also unchanged. So now let's turn this 2 into a 0. We want to have this 1 be another pivot. We're really interested in making this a pivot column to help us solve this matrix equation much easier. Just things are so much easier if we have an identity matrix. Sometimes you can't get the identity matrix. So let's just have a quick refresher on what the identity matrix is. So an identity matrix has to be a square matrix. And this is just kind of a quick segue, a quick tangent, one of my famous ones. This is an identity matrix. They must be square. And they must have only pivot columns. So these are the two main criteria for something to be an identity matrix. They must be square, and then every column must contain pivots. So this right here is an identity matrix. Satisfies all the requirements. So we can tell it's a square matrix because it's 3 by 3. If we added another column, it's no longer a square matrix because we have 3 rows, we have 4 columns. We have to have the same number of rows as columns for it to be considered a square matrix. So this one right here, 3 by 3, is definitely a square matrix. And then every column must contain pivots. So this 1 is a pivot because we have a 1 and a bunch of zeros. This is also a pivot. This is also a pivot. So we have 3 pivot columns. Every column is a pivot column. So that's the second criteria for something to be an identity matrix. And it's always our goal to get the identity matrix because it makes the system much, much easier to solve in the long run. We get our answer much quicker and much more efficiently. So I'm really interested in getting rid of this 2 right here. I'm interested in making this into a 0 so that our second column will be a pivot column. Let's talk about how to do that. So I'm going to leave the first 2 rows unchanged. We're only going to be changing the third row. So let's take the second row, multiply that entire second row by -2, add that result to row 3, and then replace row 3 with the result. Let's see if I can do this without messing up. So we're going to take row 2, multiply it by -2. We're going to add that to row 3. And whatever number we get as our result, we're going to put that back into row 3. So the 0 is going to be unchanged. So we're going to take this one right here, multiply it by -2, we get -2, and then 2 plus -2 gets us 0. We're going to take this one, -1 times -2 is +2. We're going to do 5 plus +2, and we get 7. So we're almost there. We have 2 pivot columns. We want to make this last one a pivot column if possible. So the best way to do that would be to take the entire third row, first of all, and multiply everything by 1/7. That way, this is a 1, because we need this one to be a 1 for the third column to be a pivot column. So I'm going to take row 3, divide the entire thing by 7, and then replace row 3 with that result. So the 0 and 0 are going to go unchanged, but the 7 is going to turn into a 1. So now all we need to do is add row 2 and row 3 together and put the result in row 3. So 1 plus 0 is 1. That's going to be unchanged. -1 plus 1 is 0. All right, we're almost there. Now all we need to do is take everything in row 3, multiply it by -2, and then add that to row 1. So this is a 0, so this 1's going to go unchanged. This is also a 0, so this 0 is going to go unchanged. But when we multiply this element by -2, and then add it to this element, we get 2 plus -2, which is 0. So yay, we got the identity matrix. So let's go ahead and replace this matrix with the identity, because we know this is algebraically similar to the matrix, the identity matrix. So we don't need any of this anymore. So because we know matrix A is equivalent to the identity, we can write the same exact matrix in its place, and we'll get the same thing. This is fun. I don't know if I'm crazy for thinking this, but I hope you agree. I don't know if it's sad that this is the most exciting thing I'm doing all day. To be honest, I'm just thrilled to be done with moving. I'd rather do almost anything else in the world than move. All right, so things are a little easier to handle now. So we have A plus 0B plus 0C equals 6 for our first row. Second row, we have 0A plus 1B plus 0C equals -4. And then we have our third row, which gives us the following. We have 0A plus 0B plus C is 7. So this is why the identity matrix is such a great thing to have. It explicitly tells us our solution. It tells us right away that our solution is 6, -4, 7. So that is what a solution looks like. So remember what we set out to do. We set out to find vector x. Oh, I made the notation wrong. So it's a vector. So we either want to use the angle brackets or we want to use column vector notation, which is this one, components lined up in our famous column vector notation that we like so much. Or we could also do it like this. We could say this is going to be 6 times I hat plus -4 times j hat. But because this is in the third dimension, we're going to have a k hat this time. It's going to be plus 7 times our k hat unit vector. So remember, a unit vector has a length of 1. So if this vector has a length of 1, this vector has a length of 6. And then this vector has a length of 4. I know we have a negative there, but when we're talking about the length of a vector, length is a magnitude only. We don't care about negatives. I don't know about you, but I've never seen a ruler with negative numbers. We can't measure negative distances. So that's why when we're talking about the length of a vector, we don't have any negatives. So this vector right here has a length of 4. And then this vector has a length of 7 because k hat has a length of 1. 7k hat has a length of 7. So I hope you all enjoyed this as much as I did. In the next video, we're going to be going a little more in depth on certain properties of vectors. We're going to be talking a little bit more about vectors before we apply them to more complicated matrix situations. We're going to learn a bit more about adding complex vectors together. I don't mean complex in the imaginary number sense. I mean things that are a bit more complicated than we're used to. We are going to talk about finding lengths of three-dimensional vectors and some other things I don't want to spoil for you right now. So hope you enjoyed this. See you guys in the next video. See you later.